Okay, in that last video we finished up talking about position vectors, or at least introduced them. As I mentioned, we're going to work an example problem here. This is fundamental problem 219. I'm working out of the Hibbeler text, 14th edition. Set this up here. That's what I'm using in the course I'm currently teaching. We're going to work this problem, though. I'm going to draw it just a little bit different than how he presents it there. I'm going to show you as I go. This is, again, out of the Hibbeler text. This is fundamental 219. This is going to be lecture 3, page 2 of something. Now, if you look, I don't particularly care. You'll find a lot of texts will measure points this way. I don't particularly care for kind of labeling it this way. This is what I prefer to do. I'll show you kind of how I draw it, and then we'll compare. I'm going to draw. What we're trying to do is we're trying to describe a cable connecting 2 points, points A and B. A down here to the left, B up and to the right. It uses a standard XYZ configuration. I say standard where we're using Z up and down as vertical. Y, this one kind of goes out quite a ways over here to the left. Y left to right to left is Y. And then X just kind of coming off at an angle here. Okay. Now, point A is over here. It's in the XY plane. It has no Z value. If you look at the way it's measured, it's a little confusing the way they draw it, in my opinion. It's 3 meters out in the positive X direction, and it ends up being minus 2 meters in the Y direction. That's point A. Again, I don't particularly care. You see how they've drawn it here. And this is correct. There's nothing wrong with it. I just find this is not as clear as this. Where here, if I say, all right, well, A is right here, 3 meters out on the positive X. It's minus 2 meters in the Y. And it has no Z value. And this is just in the XY plane. And then B is out here. It's up in the, it appears to be, no, this actually has X, Y, and Z components. Point B does. So we'll draw it out there. Looks like it's got a negative X component. So it is out here. Point B is out here somewhere, we'll say. It is, when you look at it, it ends up being a positive 4 meters out here on the Y-axis. It ends up being in the negative X direction. It ends up being minus 3 meters in the X direction. I've not drawn this super well. And then, if you follow it along to where it measures on the Z-axis, it measures a positive 3 meters up on the Z-axis. That's point B. Again, that's the way I prefer to draw it. I think that's less confusing. This is okay. They're showing you it's 4 meters out here on the positive y-axis. They're showing it's 3 meters back in the x direction, so negative x direction, 3 meters, and it's 3 meters up in the z direction. My preference is to draw it this way, but either way is perfectly fine. It makes me no difference. Draw it the way is helpful to you. Again, to connect those two dots, I'm going to dot a line kind of gently in between them. So if I dot as I go, then it's a little bit easier to connect those dots than it is to just, I mean, if you can freehand a straight line between those 2 points, man, go for it. Right? And maybe there's a career for you doing other things other than engineering. I don't know. But now I've got a cable now connecting points A and B there. Okay. It's a lot of time to set up a problem. Yeah, 3D problems do take a little while to set up. The problem is asking us to determine what they call the Cartesian. That's describing a Cartesian vector system where they're saying X, Y, and Z, or Cartesian coordinate system where they're saying determine the Cartesian. That means X, Y, and Z components of the vector connecting points A and B, the position vector between A and B. And determine the magnitude and direction angles. That's the alpha, beta, and gamma angles. And I'm going to add a step to this one. We're going to do a bonus step. Bonus. If there is 1 kilonewton or 1,000 newtons of tension in this cable, determine the tension, how much of that tension is in the X, Y, and Z direction. So this is what we're going to do. And it's a little more than the fundamental 219 problem asked for, but that's okay. It's easy enough. My chair makes funny noises when I move around. That's not bodily functions. All right. So what do we do here? Well, this is what I like to do when I work. This is a problem using, I'm going to need to use position vectors. What I like to do is I like to make sure I know the X, Y, Z components or coordinates of each point involved whenever I have to build position vectors. So point A, for example, is out here at a positive 3 meters in the X direction. It's at a minus 2 meters in the Y direction, and the Z direction is 0 meters. It's in the XY plane. So it's not up or down, it's right on the XY plane. Point B has a minus 3 meters X value, minus 3 meters X. It has positive 4 meters in the Y. And it is up 3 meters in the Z direction. So those are the locations of point A and B. So I find if I write that out, that makes it a lot easier to write position vector between points A and B. Because again, as we mentioned last time, if I'm describing a position vector between 2 points, going from point 1 to point 2, I'm just going to take final minus initial of the X, Y, and Z values. So this needs to be final minus initial in the X direction. So I'm going from A to B. So if I go from A to B, that means my final value is minus 3. And my initial value, so I'm going to subtract from that final value a positive 3. That's going to be meters in the I direction. Both of them are meters, so I'm going to factor that out. And that way I only have to write the units once. You could actually factor it out the whole thing and write it one time, but that's another story. All right, add to it now the Y component. So again, final minus initial, I'm going from A to B. So I'm going to end up at B. That's a positive 4 in the Y direction. Minus a negative 2 is where I start from. So it starts out in minus 2 in the Y direction. Those are both meters, and those are both in the J direction. And then finally, add to it the Z components, final being 3 meters. I'm going to point A, subtract from it the initial Z value, that's 0. Those are both meters, and those are both in the K direction. So now my position vector from going from A to B is minus 6 meters in the I direction, plus 6 meters in the J direction, and then plus 3 meters in the K direction. Or if you like, you can write, you could also say, well, that's minus 3I plus 3J, minus 6. I got ahead of myself. Minus 6 in the I, plus 6 in the J, plus 3 in the K, and those are all meters. Either way you want to write that is perfectly fine. All right, now does that make sense? If I'm going from A to B, that means to get from A to B, I am going to move 6 meters in the negative x direction. That's what I have here. I'm moving minus 6 meters in the x direction. I'm moving plus 6 meters in the y direction to get from A to B. So that's plus 6 meters. And then I'm moving up 3 meters, positive 3 meters in the k direction. That makes sense. Okay. The problem said, what are the Cartesian components of that vector? That's this guy. That's correct. That's one answer. It wanted us to also find the magnitude and the direction angles. That's the alpha, beta, gamma angles. Well, the magnitude's both those are pretty straightforward. The magnitude is where you take the square root of RA in the x squared, or RAB in the x squared. You take its x component squared, add to it RAB in the y direction squared, add to that then RAB in the z direction squared. And you take the square root of that whole thing. So that's going to be the square root of minus 6 meters squared plus 6 meters squared plus 3 meters squared. I'm going to skip some steps here to skip as many or as few steps as you're comfortable with. It's 36, 72 plus 3 more makes 81. I did this earlier, so it's fresh in my mind. That's 81 meters squared, because each of the meters gets squared, so that's 81 meters squared. Square root of 81 is 9. Square root of meters squared is meters. The magnitude, the length of the vector, to get from here to here, the length of that is 9 meters. And these are the components in each of the directions. Now to find the angles, if I go back to my lecture 2 notes, it's the last thing I covered there. Here's my lecture 2 notes. Remember, if I know the x, y, and z components, I can divide by the magnitude of a vector and take the arc cosine, and that would give me the angles, each of these angles for that vector. So what I can do is I can say, well, alpha, the angle between that vector and the positive x-axis, is going to be the arc cosine of, this is going to be r ABX divided by RAB, the length of RAB, which we now know is 9 meters. That's the length of RAB, the magnitude. So that's one answer it's also looking for. And if I take the arc cosine of this quantity, so this quantity is minus 6 meters divided by the 9 meter length, and you take the arc cosine of this. I know I should write it in different order, flip those. I'll let you do that in your calculator. And in fact, let's write them all out, and then we can do all those in your calculator. So beta is going to be the arc cosine of then the y component divided by the 9 meters. So the y component is a positive 6 meters divided by the 9 meters. And that's going to give me that angle. And then the gamma angle is going to be the arc cosine of the z component. That's a positive 3 meters divided by 9 meters. Take that ratio and take the arc cosine of that. And that'll give you the gamma angle. That'll be, so this is the angle between the positive x-axis, the positive y-axis, and the positive z-axis to this vector here. So go ahead and pause, find those values, and come back. Got them? Good. So I got, and this checks out with the solutions in the back of the book, 132 for alpha, 48.2 for beta, and 70.5 for gamma. And then I asked a bonus. I said, if there is 1,000 newtons of tension in this cable, let's say I've got a cable connecting these 2 points, and if I've got 1,000 newtons of tension in the cable between A and B, what is the x, y, and z components or amount of force in the x, y, and z direction in that cable? Well, the tension in a cable from A to B, right? The tension in a cable from A to B would be the magnitude of that tension, AB, times a unit vector that goes from A to B. We can find a unit vector by taking the position vector from A to B, which I know, divided by the length of that position vector, the magnitude, which I also know. This guy, this is the magnitude. This is the position vector here. So I can take this ratio and it's multiplied by, let's say this times this, not equals. And so I can do that. I can say if I take 1,000 newtons times this vector, well, this is going to be minus 6i plus 6j plus 3k. These are all meters divided by 9 meters. Next page. And then very soon, next video. You can run these out. Pause here if you like, if you want to run the calculations. Got the answers here. This is going to be minus 667 in the I direction. Let's put newtons all in, let's just write newtons once. Plus 667 in the J direction. Plus 333 in the K direction. And these are all newtons. So this tells us how much force would be in each of the directions. About 667 newtons in the negative X direction and the positive Y direction, and about 333 newtons in the positive Z direction. All right, I'm going to stop this video there. It's a little more than 15 minutes, but that's okay.